It's open because it's open on Sunday also. So I'm thankful to Markus for coming for very short notice. And so he did PhD from Göttingen. It is a very famous university in Germany. Actually, it is one of my favorite university town, you can say.
Okay.
And now he is doing postdoc in Oxford. So he will talk about like gauge theory and something like that.
Okay, thank you very much for the invitation. Thank you very much for coming, everyone. So I have only very limited time, and I had only very limited time for preparation. So I've decided to discuss one particular aspect of our work, which is a very interesting tool to study differential equations. So I'm going to introduce a certain nonlinear partial differential equation. So you should think this is something very hard to solve, and discuss how you can solve this using methods from algebraic geometry. It's very fascinating connection there. Okay. Now, to formulate these equations, I'll have to introduce some background terminologies. These are not differential equations just for a function, a usual function, but for some generalization of a function. That's the first thing I'm going to introduce. Part of the vector bundles. And maybe just as a motivation, let's look at a space M. You can think of a function which takes real values. And this means that f of p is going to be a real number. That's an ordinary function, right? You put something in, you get a real number out. Now, the generalization that I'm going to be interested in, ordinary function, is called a section. And it's a little different in that the value, s of p, now doesn't belong to one fixed codomain, but this target here can change with the argument. So s of p will be an element of some set E of p that depends on the argument p. Okay. And so the first thing I'm going to explain is what are these E of p's. They're going to form what's called a vector bundle. All right. So let's start very basic with a definition. Let's say M is a set. Very basic. And then I want to explain what a family of vector spaces is. So this is meant to be some parametrized version of linear algebra. In linear algebra, you have one vector space. Here we have a continuous family of vector spaces. So a family of vector spaces consists of two things. First of all, it's going to be a set E. Then we're going to have a map to M, and then I'll call this map pi, and I'm going to use the notation that EP is the pre-image of a point under this map. So let's maybe draw a picture. You should think something like this could be E. This means that it extends infinitely in this direction. and this would be the set M. And the map simply takes this point, this point, this point, and this point. So this is the fiber which gets mapped to here. So that would be P. And then this would be the pre-image of the point P, which I also write like this. Or sometimes I will also put something like this. E restricted. Okay, A and B. And well, so far it's just a family of sets. I want it to be a family of vector spaces. So the third piece of data we require is the structure of a vector space on each of these. So this, for example, this in the picture, this is a vector space. It's just a copy of the real numbers. It's a one-dimensional thing. So let's see. We also require vector space structures on E restricted P. So recall that this means that you have a map plus. You can add any two elements, and you have a scalar multiplication by the real numbers. This satisfying the usual actions for a vector space. If I have a vector here, I have a vector there, you can W, and you can add them, you can scale them, and the usual things. And there's also in every vector space, there's one special element, the zero vector. This is what this indicates here. So there's also 0, and I'll call it 0P because there's a 0 of this vector space. This is another vector space, there's another 0. So there are lots of zeros. And all of these zeros make up what is called the zero section. This is what this line here. So I should maybe give you a reference. So my favorite reference on all this material of linear algebra, which is kind of parametrized by a space, is a very nice book by Michael called K-Theory. It's very easy to read. There's you this one. Okay. All right. So this is an example. But so this definition still allows that the dimensions of these vector spaces can jump as you move around. There's no requirement about the dimension of the vector space or that they deform in a continuous way to each other. So you could imagine that you just that it just goes on, and then you add some higher dimensional spaces over here. This is allowed over here. For a vector bundle, this is not allowed. So this is something which is weaker than the definition of a vector bundle. Right. So let's see now the definition of a vector bundle. So this is not quite as general anymore. We want to say what it means for these vector spaces to deform continuously, not to jump. Like here, there's a jump from this is a one-dimensional vector space, and then it jumps to 2 dimensions. This is bad. Now we want to explain continuous, so we need to make a requirement that M is going to be a topological space, so that continuous makes sense. And all right, so a family of vector spaces. So I usually just write E over M, and this structure is understood. Write family of vector spaces, E over M, is called a vector bundle. paper together with a topology on E. It's called a vector bundle. If the following condition is met. Every point in M admits a neighborhood U of P. So this is an open set in M with P in U, and a homeomorphism. So recall that this is bijection, which is continuous, and the inverse is also continuous. A homeomorphism H from, I think I wanted to go this direction. U cross Rn to E restrict U, which by definition is just the pre-image. So I'll draw a picture in a second. And the homeomorphism with two properties. First is that so if we go over here, then we're here, and then we can project down using the map pi. If we project down using pi, we get a point in U. So compose the map H with the map pi, I get into U from here. And another way to start here and to get into U is just to project onto the first component. So the first requirement is that if I go over, project with pi, this is the same as projecting to U immediately. The second condition is that HP with a variable second argument, this is a map from Rn to E restrict P, this needs to be an isomorphism. Our linear isomorphism for all P in U. That's a picture. So feel free to ask questions if anything's unclear.
I have just to comment. Some of the students here know what is sheaf.
Okay.
So maybe you can try to use that word.
There is a relation, yes. So these are very special kinds of sheaves. Just quickly draw a picture and then I'll comment on the sheaf. So the idea is that a vector bundle maybe looks something like this. This could be E, M, and it's some kind of twisted product. But locally, you can always identify the vector bundle with untwisted thing. So this is, let's say M is larger, and this is just U. And then this could be E restrict U. This is this part of the vector bundle. And this is a picture of U cross Rn. So n is 1 in this example. And then you just have the obvious projection onto the first component, which just goes down here. Projection down over here. And the homeomorphism identifies this part of the vector bundle with a trivial product U cross Rn. It is done in such a way, that's requirement B, that the vector space structure on each fiber here, so that's just Rn, gets identified with the vector space structure on these fibers, E restrict P. Alright. Now, maybe briefly comment on the relationship to sheets. Erase this again. So, to explain this, we need to introduce one more idea, which comes back to the beginning. So in the beginning I said that we're going to introduce a generalization of functions, right? Generalization was a section. So let me now introduce this section and then tell you how this gives rise to sheets. So a map from M to E is a section called a section. Okay. Very simple. I composed with S. So this is a map from M to E. This is a map from E to M. The composition goes from M to M. This is required to be the identity. Okay. And this is a generalization of the function of the following reason. Here's a very easy example of a vector bundle. So we can take E simply to be M cross Rn. For example, n could be 1, M cross R is in the picture. And then to get the vector bundle, we have to provide this projection here. Then for I E to M, well, E is just M cross Rn. So we just use the projection onto the first component. And if M is a topological space, or N is a topological space, we can put a product topology on E. This is the one we use here. And then for the product topology, the projection is a continuous map. So that's good. And then I need to check that this condition here is true. So every point has some neighborhood. And in this case, it's very easy to check this condition because you can just take U, usually it's a very small neighborhood, but in this example, we can take U equals to the entire space M. And we need to write down a homeomorphism from E restrict M, so this is just E, because the inverse image of everything is everything. We need to write down a homeomorphism of E to M cross Rn, which is extremely simple here, because E is already M cross Rn, so this is simply the identity now. And then you can check that these conditions A and B are satisfied. And in this case, a section E, well, E is M cross Rn. Well, a map from M into M cross Rn has two components, right? So you can write it down. And the first component, let's maybe call it E. And let's call the second component F. This means that E is going to be a map from N to M, and F is going to be a map from N to Rn. And the section was not just a map, there was one requirement. The requirement was that if we compose with the projection, we get the identity. So what does this mean? Pi compose with S. pi was just the first coordinate projection. Written S in these components, so if I compose this with the first coordinate projection, I just get E back. And the requirement for a section, this is because S is a section, was that this is the identity. So we find that the condition for an arbitrary map from M into M cross Rn to be a section is that this E component is actually the identity. Yes. And in this way, let me summarize that sections S of the trivial bundle, M cross Rn, with its obvious projection into M, these are in one-to-one correspondence with vector valued functions on M. So this particular easy example of a vector bundle shows that these are really generalizations of vector valued functions. So you could take n equals to 1 or real valued functions. Right. And now you can define, let's have this maybe as a remark. E over M be a vector bundle. And then you can define a sheaf of this. You define sheaf of equal groups. And recall that a sheaf associates to every open set U a abelian group. And the abelian group I will use here is the set of all sections E restrict to U, which is a vector bundle now over, and if you let U vary, you get a sheaf. You can add sections because we have this operation of addition on the fibers of E. We can add them, and even more than just a sheaf of abelian groups. It's actually a sheaf of modules over the smooth functions, continuous functions in our discussion on M. That's just an aside. And it is actually an equivalent point of view where you can say that a vector bundle is the same thing. Say that a vector bundle is the same thing as a locally free sheaf of where this is the structure sheaf of M, which could be the sheaf of continuous functions on M. This is just a remark for those who know what a sheaf is.
Fixed rank.
Fixed rank. My rank is always fixed. I might add that. It's called the vector bundle of rank N. And then we should take rank N here. All right. So, but of course, there's no point introducing such a definition if I want to go beyond the usual functions here. So let's have a look at a non-trivial vector bundle. This is a trivial vector bundle. Here I have just a problem. Just erase this. Okay, so first non-trivial example is the Markus pattern. going to be a vector bundle over a circle. The circle I will write now as 0, 1, just a unit interval with the endpoints identified. This is an equivalence relation, which is generated by the condition that 0 is equivalent to 1. So, of course, for an equivalence relation, you need to have it's transitive and reflexive, symmetric. So, what I mean by generated is you take the smallest equivalence relation, which satisfies that 0 is equivalent to 1. So, in particular, 1 needs to be equivalent to 0, everything needs to be equivalent to itself. And such a quotient always has a natural topology called the quotient topology. And this M here, well, what happens if we take the unit interval and we take these 2 points together, well, we get a circle. So this is a homeomorphic to the circle. And the Möbius band is, I'm sure you've already seen a picture. So I didn't, there's a good reason I didn't become an artist, but I'll try. To draw Möbius band for you. Something like this. Möbius band. And this is, of course, this extends infinitely each of these lines, but I can't draw this. This will destroy the picture. So this is E.
Markus.
Yes. Oh yeah, very nice. Maybe you should just pass it around. Then here we have the Möbius band already. Very nice. And mathematically, so I'm not an artist, but I'm a mathematician. So I can write down a formula for E, which is in the same spirit as here. It's just 0, 1 cross R with an equivalence relation called equivalence 2, which is now generated by the point 0 x is equivalent to 1 minus x. The picture of this is this is R, this is 0, 1, and then we identify this thing with that. So these points are identified, or these points are identified, or these points are identified. And if you do it, you get exactly, this is how you do it by hand. So this is E. And because the way the equivalence relation is, there is actually a well-defined map into M, just given by projecting onto the first component. So we need to check that this factors through this equivalence relation. All right, and maybe now as a warm-up, have a small proposition about the Möbius band, which is that every section of the Möbius band, so it's map from M to E, has at least 1, 0. So we have some colors. No. Yeah. Right. So, in the same way as over here, where we just identify sections of the trivial bundle with ordinary functions, we do the same thing in this setup of the Möbius band. We find that a section corresponds to a function which takes opposite values here. So something like this. This would be a section. And, so, this. functions on 0, 1 are with the additional property that f of 0 equals minus f of 1. If you unpack the definition of section, you'll find that this is true. And, well, let's say without loss of generality that f of 0 is actually positive. So if f of 0 is 0, then we're finished. That's clear? So it's positive or negative, let's say positive. Okay, then f of 1 is equals, and this here, minus f of 0, so for negative. We have a continuous function, f is positive at 0, negative at 1. Remember our basic mathematics, there's the intermediate, what is it called? Intermediate value theorem, not probably theorem, which says there exists t in 0, 1 with the property that f of t equals 0. Okay.
Nothing, just intermediate value theorem. F is continuous and
Yes. Yeah. So let's make that a small picture. This is 0.
Derivatives
F
on the rules here.
is x.
that's the whole thing. This is simple.
0 is 1. And then, well, set it as positive, it should be negative. So if it's continuous, you must go. All right. So let me just maybe remark that everything we discussed so far, I discussed in the setting of topological spaces. But you can do the same definitions and assume that M is a smooth manifold, for example. The total space is also a smooth manifold. Or you can apply the same definition for complex manifolds from the holomorphic world. So in this case, you would require the map H, which we have here. It's called local trivialization, to be holomorphic, biholomorphic. So all of this carries over to these situations. And I was going to discuss differential equations, so I need at least a smooth manifold to do this. So from now on, everything is going to be polar. Manifold. Second part, beyond connections. It's the first part of the title, permission endless connections. So here, M is required to be a smooth manifold. And if you don't know what that is, you can just say M is R. That's fine. R1, just the real lines, depending on how advanced you are. Maybe this is difficult enough for you. So recall that this means that, well, there's a picture of a smooth manifold, Riemann surface. And this means that locally, globally it's maybe a very complicated object. But locally, you can always introduce coordinates. Always, it's called a chart. X1, X2. And you can describe the manifold, so this is a picture of the entire manifold M. Locally, we have coordinates. Locally means on a sufficiently small open set. Coordinates. Just as in the usual case of Rn. So coordinates are going to be called xi if we have a usual smooth function from n to r, depending on your level of sophistication, you could say a function from r to r, or from r2 to r or something. We have a notion of taking the derivative of the function. So, for an ordinary function, you have df of dx1. So I always write the 1 in the upper. Let's say putting a 1 down here, just to make it agree with the Einstein summation convention, which is used a lot in differential geometry. So you can take all these derivatives, and these are going to be real numbers. Okay? And the differential equations I want to discuss, I mean, they must involve derivatives. That's what differential equations are about. They would be for sections. And therefore, I have to explain how to take the derivative of the section. And so, let's see how that goes. So, what about sections? That's the question. How do you take the derivative of the section? And, well, to discuss this question, let's maybe let's choose an open covering of n. To alpha, we're going to open coordinate neighborhoods. This means we can introduce coordinates there. And also, a vector bundle was something which was locally just a product. So we can choose an open covering of M, so that locally we can write our vector bundle just as U alpha cross R N. Let's call this map here H alpha. The idea is that now maybe we have a vector bundle, this, with, so maybe this is U alpha, and this part would be U beta. This is an open covering of that, so we have some intersection here sometimes. And over this part here, you can identify your vector bundle using a trivialization H alpha with U alpha cross Rn. And on this part here, you can identify it. So this is, unfortunately, we don't have color. So this part is identified with U beta cross Rn in a possibly different way. There's not one way just to make a vector bundle trivial, but we can always choose ways, right? And, well, on the overlap, so the overlap, U alpha intersect U beta, we have, we can go from U alpha cross Rn into the vector bundle, and then we can use H beta to go over here again, to go from U alpha cross Rn to U beta cross Rn over the intersection. And these two maps, the first component is always the identity, and the second component is a linear transformation from Rn to Rn. We know what that is, that we usually write as an invertible n by n matrix over R. So we have these G alpha beta maps, so that H alpha equals G alpha beta times H beta. Well, at least restricted to, this is the common of U alpha cross U beta. Okay. So, right. So the first idea might be that we can use H alpha to turn our bundle into a trivial bundle. And we said that sections of a trivial bundle are functions, right? And we know how to take derivative of a function. So let's try this. Now, a bit more formally, I have to write H alpha composed with the section S. So S is a map which goes into E. And if I use H alpha, I get into U alpha cross Rn. So let's just forget about the U alpha part, since that part is just the identity anyways. So this is, I would think of as a function from U alpha to Rn. This is what I earlier called F. So locally, a section corresponds to a function. And so we might say this is F alpha. So U alpha to Rn. And well, so if we use the trivialization H alpha, we get the function F alpha. If we use H beta, we get a different function, F beta. And there's some overlap where there are two conflicting definitions. We have F alpha and we have F beta. And the relationship is quite simple. So F alpha is this, and then from over there I have this was equals to G alpha beta times H beta composed with S. So this is simply G alpha beta times F beta. So in general, you can describe a section of a vector bundle by making it locally trivial, so choosing these trivializations here. It's called trivialization. And then you will describe a section by a family of functions. So we have an F alpha function for every alpha in A, which are on the overlap related by this formula here. Now the idea was to say, well, why don't we just take the ordinary derivative of these representing functions F alpha. This doesn't work. So let's try it. So I want to take d f alpha by dx I. It's going to be another vector value function. Actually, but we can take the derivative at the point, but I'll just omit this point here. This is a vector value function, and we could convert it back to become a section by applying this H alpha inverse. The H alpha was used to take a section to a function, H alpha inverse was the opposite. So this might be a definition, but there's a bit of a problem here, because over U alpha intersects U beta, there are two possible definitions. We could take this as a definition, or we could take this as a definition. So if these are not equal, then it's not well defined. Okay, so let's calculate. Let's see if they are equal. So this is H alpha inverse. Well, H alpha I can write as G alpha beta times H beta. So this is simply this. This is from over there. And then F alpha is equals to this product, so I need to apply the Laplace relative. And I get dg alpha beta dxi times f beta plus g alpha beta times df beta by dx. Okay, and so maybe take this part of it. So these two together, this and that cancels. So we get exactly this. This looks nice, but there's of course this additional term here which is disturbing. So this is plus G alpha beta inverse G alpha beta by dxi, and these two I can combine, H beta inverse F beta. This is simply S again. Right. So these are unequal together, except that this is 0. Sometimes it is 0. Then you have what you call a flat connection. But in general, it's not 0. Okay, so it seems everything's over. There's no way to find derivative. As always in mathematics, you can turn a problem into a virtue. So you realize there is this problem, and let's see how to fix it.